Digital gates with nanotechnology. If you look at a magnet, it'll have a positive side and a negative side, which will be represented by the N here for north, and the S here for south will be the negative. And it'll have magnetic waves that will go from the north to the south. If we position three magnets next to each other, what will happen is the positive will be attracted to the negative, and two positives next to each other will repel from each other. If I apply that, and what I do is I take an atom that is positively charged and I attach it to a pivot point. Take another atom that is positively charged and attach it to the same pivot point. What will happen is they'll be on the exact opposite sides because they're repelling each other, but they're still attached to the pivot point. If I rotate one, it'll rush the other one to the opposite side. We can look at that as a standard building block in nanotechnology. So if I take it and I use that as sort of a chip setup, and I put one right next to it that has the exact same setup, my positive will be attracted to its negative space, and this positive atom will be attracted to this negative space. Also, when we have two positives next to each other, it'll cause the one on the side to rotate. And we can use that to transmit a value. So if I rotate this one here, everything will rotate in relationship. If I rotate this back, everything will rotate in relationship. Where this can be interesting is if we assign a logical or a binary value to each of the chips. So if the positive is in the top left, we'll call that a binary 1. If the positive is in the top right, we'll call that a logical or binary 0. We can then have a logical value that can transmit itself through a series of these chips, and it can make turns if we need it. To develop a digital gate, we can develop an inverter by having a 1 coming in and a 0 coming out. If it changes to a 0, the 1 will come out, giving us an input that is always the opposite of the output. In nanotechnology, we can do this by having our series here of 1s transition to a series down here where we have an offset of a half a space. Then what will happen is if we transition it here, they'll all go to 0, changing these all to 1. So again, the input is always going to be the exact opposite of the output. With an AND gate, what we will see is if we have two zeros, the output will be a 0, a 0 and a 1 will be 0, a 1 and a 0 will be 0, and when this and this are both 1, my output will be a 1, which will follow this truth table. If I want to represent this in nanotechnology, what I can do is I can have an intersection with 3 branches to it. And notice right now that all the branches are the same. This is our output, by the way. So they're all 0, so what's going on is this positive is attracted to this negative, positive, negative, positive, negative, positive, negative, positive, negative, and positive, negative. Everybody's happy, right? And notice we have a set state down here, so these will always be 0. If I transition this one, right, so we have a 1 coming in, a 0, and our set state, which is 0, the 1's going to be telling it to transition to a 1, but these two are going to be saying, stay a 0. And what will happen is, since majority wins in this type of setup, it will end up staying as a 0. So we can see that our truth table is sort of filling out the way it should. If our B transitions to a 1, our output will change to a 1. So when A and B are both 1, our output will be a 1. Because again, the majority of the A and B is forcing this to be a 1 or pushing it to be a 1, even with our set state of 0 there, because majority wins again. For an OR gate, we have two zeros equals 0, a 1 and a 0 equals a 1, a 0 and a 1 equals a 1, and 1 and 1 equal 1, giving us this truth table. We can represent the same thing with a similar intersection. Notice we have our 3 branches again. We have A here, which is set to 0, B here, which is set to 0, and our set state which is set to 1. Notice in this situation, though, not everyone is happy right off the bat. So we have our positive, subtractive, negative, positive, negative, positive, negative, positive, negative. And down here, our set state is not happy in this situation because we've got a positive next to a positive and a negative next to a negative. If I transition this A, though, to set it to be a 1 value, we now have this one and this one. So the majority of my inputs saying to be a 1, so this will transition to being a 1. And if I transition my B, right, we have all three, both of these are 1s, so my output will be a 1. We can take these principles and develop standard AOI logic circuits in nanotechnology.